Uh, Hi everyone, good evening to all attending here in India, and a very good morning to our speaker joining us from Chile. Welcome to the second week of our winter school on deep learning and to the second plenary session. Last week, our plenary speaker, Professor Martin Grohe, brilliantly explored the logic behind GNNs. Tonight, we continue this journey with Professor Pablo Barceló from Universidad Católica de Chile. His current research has brilliantly eh, contributed to bridge the gap between modern deep learning architectures and the classical foundation of logic and complexity theory. To chair tonight's session and to introduce our distinguished speaker, we are delighted to welcome Professor Arijit Ghosh. He is an associate professor in Advanced Computation and Microelectronics Unit from Indian Statistical Institute. His expertise in theoretical computer science makes him the perfect guide for this evening. Over to you, Professor Ghosh.
Yeah. Thank you. It's a privilege to introduce Pablo Barceló today. So we are very happy that he has agreed to give a talk in this school. so so he's like a very accomplished speaker, like computer scientist. So I will try to keep his intro short. Okay, I want people to hear him, not me. Okay, Professor Pablo Barceló is a professor at University Católica de Chile and a director at the Institute of Mathematical and Computational Engineering. He's also principal researcher at two institutes, Millennium Institute for Foundational Research on Data and National Center for Artificial Intelligence. His research is in the intersection of logic, database theory, and machine learning, with seminal contribution to theoretical foundation of modern neural architectures. And he's particularly known for proving attention mechanisms are Turing complete. So this is something which is very interesting because uh, there was a point few years back when I was hearing that neural networks are solving everything, and I could not understand why it is happening. So at least this thing made some sense why it was happening. Okay, so it's very nice to have him here today, and he will be talking about the role logic plays or the role logic will play in advancing modern machine learning. Thank you, Professor.
Well, thanks very much for the invitation. So I'll start sharing my slides. So, okay, do you see them in as a presentation mode, or how do you see them?
I see them as a PDF. It's not
okay. One second. Now you see it in presentation mode. Okay, thank you. Well, so first of all, I didn't know that Martin Grohe was a previous speaker here, so probably there will be some intersection between the things that I'll be talking about and what he discussed, but I hope to be able to give a different focus on the kind of questions that we're looking at, yeah? People, I think that even empirical researchers in machine learning would agree with me that machine learning requires solid foundations to be fully deployable, right? In several different aspects that I will try to discuss later. And our hypothesis as theoretical computer scientists is that both the theory of computation and logic in particular, which is one of the main tools we use in theoretical computer science, can be instrumental in this endeavor. So a bit of advertisement here. About 3 months ago, together with David Solpik from France, we published a short survey on the European Association for Theoretical Computer Science, the bulletin of the European Association for Theoretical Computer Science, EATCS, on the current connections between theoretical computer science and machine learning. So you might be interested in taking a look at this survey. So some of the examples of the current applications of logical methods in machine learning include, well, the the good old idea of representing knowledge, right? It's very important to represent knowledge in order to have architectures that are more robust, that can learn with less data, that can generalize better, and so on. This idea of knowledge representation today has evolved into a well-known and well-established area of neurosymbolic AI. Yeah. Also understanding the expressive power of machine learning models, what these models can do and how they do it, which kind of resources they need to accomplish this expressive power. This tells us about the capacities of the machine learning models that we have today. Something that very important that has been gaining a lot of traction lately is verifying the correctness of such machine learning models. How we can verify that the machine learning model is indeed doing what we want them to do. Yeah, and this is related to the very established area of verification in theoretical computer science, and people have started to study the connections between verification theory and verification of machine learning models, in particular designing languages that can be used to express verification properties and to compile them into algorithms, yeah, that can solve these verification properties. Improving the interpretability of machine learning decisions, how we can use logic to express what are the things that we want to interpret about machine learning models. And finally, designing declarative general purpose languages for machine learning tasks, right? So we know from theoretical computer science that declarative languages are very useful, and the idea now is how we can bring them to be useful for machine learning models as well. So I saw a recent survey by Martin Grohe, coincidentally, that it's called Query Languages for Machine Learning Tasks. So it's in Google Scholar already, so you might be interested in taking a look as well. So in this talk, I'll try to focus on, as I said in the title, in 3 different applications of logic in machine learning. And in particular, I'll be focusing on 2 of these aspects: understanding the expressive power of machine learning models and designing declarative general purpose languages for machine learning tasks. Yeah. So I will start with some results we obtained some years ago on the expressive power of graph neural networks. This is the section of the talk in which there will be more intersection with what Martin was talking about. So I will rephrase some of his results in our own terminology, and I'll try to relate them to our results. So what is the motivation here? The motivation is that graph neural networks that we call GNNs have become really important in several applications where the data is structured in the form of graphs. And this includes scientific networks like chemical and biological networks, social networks, recommendation systems, semantic parsing and query answering, and today also agents, retrieval augmented generation, and so on. And the main question we ask here from a theoretical point of view is, since GNNs can recognize graph and can express properties of a graphs, which kind of properties these GNNs can express? So what graphs in our presentation will be? Graphs will be node label undirected graphs. So a graph will be a tuple G consisting of a finite set of nodes B, a finite set of undirected edges over B, E, and a function gamma that maps each node in B to some label, to some color. Yeah. So we will work with this assumption for the rest of the with this definition for the rest of the section. So a very popular model of GNNs are message passing GNNs that we call MP GNNs, which intuitively work as follows. every node of the graph is iteratively assigned a feature vector, a vector of d real numbers, right? So each one of x, y, z, w here is a vector of d real numbers. And I'm going to update the feature vector of node B here, the new embedding of B, will be obtained as follows. I will first aggregate the feature vectors of each one of its neighbors. This is all the neighbors that node B have. I will aggregate the values that these neighbors have with some aggregation function. And then the result of this aggregation, I will combine it with the current feature vector assigned to node B. Yeah? In a way that the embeddings are initialized as one-hot encodings of node labels, right? So initially, for each color, I will have a feature vector that has one feature for each color, and it will receive a one precisely when this is the color assigned to this node. Yeah. But of course, this is a very general definition, and there is a particular instantiation of this architecture, of this message passing graph neural network architecture, that it's important in results. It's a very simple version of it. So let's say that MPGNN of B, or node B, after t steps is denoted in this way. This is the embedding vector computed for node B after t steps. So we will define this inductively. Yeah. So in the step 0, this embedding corresponds, as I said, to the one-hot encoding of gamma B. Yeah. And then in iteration in step t, I will do the following. I will take as an aggregation of the values of my neighbors. These are the U's that are connected to B. I will sum them. I will just sum them. Yeah, this is the aggregation that I consider, and then I will multiply it by some matrix of parameters. Once I have this result of the aggregation, I will combine it with the current value of node B in the following way. First, I will multiply the value of node B by some matrix of parameters W1 that depends on T. And I will sum all these things. I will add a bias vector. And finally, I will apply some kind of nonlinearity on top of this. Yeah. So sigma is a nonlinear function that is typically the sine function, as I'm showing here, the ReLU, yeah, the rectified linear unit, truncated ReLU, that is exactly like ReLU, but it stops at 1, sigmoid, hyperbolic tangent, and so on. Yeah, it can be any of them, but for the sake of the presentation, we will focus on the case when this nonlinearity is the sine function. Many of the results hold for many other nonlinearities, but we will focus on this one. But the idea is that when you learn a graph neural network, you are learning these matrices of parameters and the bias vector. This is what you learn. Yeah. But we are assuming that we have this graph neural network, this message passing graph neural network given to us. So these matrices W1, W2 for each T and the bias vector B in step T are given to us. Yeah? So when message passing graph neural networks were introduced and people started studying their expressive power, they quickly realized that this expressive power is tightly related to the Weisfeiler-Lehmann test. What is a Weisfeiler-Lehmann test? The WL test. It's a test that allows us to distinguish when two graphs are not isomorphic. Yeah. So it's a polynomial time test. We can run it very efficiently. And every time that two graphs are isomorphic, the test will reply yes. But in many cases, when they are not isomorphic, they will reply, the test will say no, yeah? Not in all the cases, because of course we don't know a polynomial time algorithm for solving the isomorphism problem, yeah? How the WL test works over a single graph, yeah? Then you want to compare two graphs, but over a single graph, how the WL test works. It iteratively colors each node with a color. The original color is just the color given by the function gamma, yeah, the node labels. And then at each step t, I'm gonna update the color of B by saying the color of B is the one given by the previous color of B, which in this case is blue, and the multiset of colors of its neighbors. Yeah. So this is the new color. It's a tuple that consists of the previous color and the multiset of colors of its neighbors in the previous iteration. And I continue updating in this way until I reach a fixed point. Yeah. So what is the expressive power of MPGNNs in terms of its ability to distinguish graphs or to distinguish nodes? Yeah. So let's say that we denote in this way the color assigned to node B after T steps by WL. Yeah. So what the team by Christopher Morris, Martin Grohe, and some other people, and in parallel by these guys, proved is that the distinguishing power after T steps of any message passing graph neural network, it doesn't matter which parameters we choose for the matrices. The expressive power of any MPGNN is upper bounded by the expressive power of the WL test. That is, if we could distinguish two nodes by some MPGNN, we could distinguish them already with the WL test. Yeah. So MPGNNs cannot distinguish more nodes in a graph than those distinguished by the WL test. And in turn, there exists a way to adjust the parameters over this graph, yeah, to adjust the parameters of the matrices of the MPGNN in such a way that the nodes distinguished by this resulting architecture are precisely the ones that can be distinguished by the WL test, yeah, in T steps, yeah. So I hope this is clear. I guess that Martin also explained this to you in the last session. But this allows us to start also connecting MPGNNs with logic, yeah? And let's think of logic over color graphs. This will be first order logic, our standard first order logic, FO. And we will have unary symbols for the node colors. So we will have red of X, blue of X, and so on. We can say that a node has this color. And a binary symbol E of XY that represents the adjacency relationship between nodes. Yeah. So for example, if I say that there exists an X, a Y, and a Z such that X and Y are adjacent, Y and Z are adjacent, and Z and X are adjacent, and X is red, what I'm saying is that there exists a triangle in the graph for which one of the nodes is red. This is one of the properties I can express in first order logic. So it happens to be the case that the WL test is tightly connected to a fragment of first order logic over color graphs. So let's say that C2 is the two variable fragment of first order logic over color graphs extended with what we call counting quantifiers. This is a quantifier that allows us to say that the number of A's that satisfy formula phi is at least K. It's at least 3, it's at least 4, whatever I want. This is a constant, right? Of course, if this is a constant, we can always express this in first order logic itself, yeah? But we can only do it at the cost of increasing the number of quantifiers, the number of variables, yeah? And this is the C2, this is the two variable fragment. So here we have the two variable fragment of first order logic, but we allow to have this extra expressive power given by these counting quantifiers that count the number of elements that satisfy a unary formula. So for instance, this is a C2 formula. I can say that X, X is a node that has at least 3 neighbors, Y, that are red, and none of these neighbors has a blue neighbor. And notice here that X appears free here in the formula, and here appears existentially quantified. And this is a trick that we often use in order to reuse the variables and use less variables to express interesting properties, yeah? So I want this to use only 2 variables, so the only way in which I could do this is by reusing X here to talk about the neighbors of Y, yeah? On the other hand, this is not a C2 formula. Why? Because it mentions 3 variables, yeah? So let's say that C2T are those formulas from C2 in which the quantifier depth of the formula is at most T. I mean, like if the formula doesn't use any quantification, then its quantifier depth is 0. And any formula any formula of quantifier depth T is Boolean combination of existential quantifications over formulas of quantifier depth at most T minus 1. So every time that we use an existential quantifier, we're increasing the quantifier depth of the formula. And for a graph G and 2 nodes U and B, we are gonna say that we are gonna denote in this way the fact that node U and node V are indistinguishable by formulas with 2 variables and quantifier depth T. So any formula phi in this fragment that holds in U over G also holds in B over G. Yeah? So a famous result by Say, Führer, and Immermann in 1992 established that the distinguishing power of WL is exactly the same as the distinguishing power of C2, of this fragment of first order logic. In particular, for every T, if 2 nodes are distinguishable by WL, then they are distinguishable by a C2 formula with quantifier depth at most T. And conversely, if 2 nodes are distinguishable by a first order formula of quantifier or counting 2 variable formula, first order formula with quantifier depth T, then they also can be distinguished by WL in T steps. In a way, what this is saying is that WL is capturing the type of this node under this logic. Yeah, the quantifier depth T type of every node. So now we get, as a corollary to the previous result relating MPGNNs and WL, a characterization of MPGNNs also in terms of logic. Yeah? So for nodes U and B in a graph G, any MPGNN, the distinguishing power of any MPGNN is upper bounded by the distinguishing power of C2, yeah, with the same quantifier depth as the number of iterations. And there exists a way to adjust the parameters of the MPGNN in such a way that it achieves exactly the same expressive power as C2. Yeah, so we have rephrased the previous result, and instead of having this algorithmic characterization based on the WL test, we now have a logical characterization, which nodes can be distinguished by formulas in the graph. Yeah? So by the way, I don't know how do you do it with questions. I mean, like, I should take them at the end. I don't know if people are allowed to ask questions in the middle.
So if I find questions, I will ask you.
Okay. So I mean,
In
just
the
that
end, I will
people
obviously
can,
ask you.
yeah, people can feel free to. They can even write them in the chat if you want. Yeah.
Sure.
In any case, since I have like three sections, and I don't know if I will be able to show them all, I will stop after the first section, so that questions can be more focused on this. Yeah.
Sure.
Now, what is the caveat of these results? They're very interesting, of course, but they tell us when two graphs can be distinguished. But they don't tell us which properties of graphs can be expressed with graph neural networks, right? So in a way, what we say is that previous characterizations are non-uniform. For instance, the matrices that capture WL or that capture the type, the C2 type of a node depend on the size of the graph. Yeah, if I change the graph and I change its size, then the parameters, the matrices of parameters will change. Yeah. And the formula that distinguishes U and B when they are distinguishable is constructed from the underlying graph. So for every graph, there exists a way to adjust the parameters. There exists a formula and so on. But for every graph, there exists one, yeah, a different one. So the question that we asked ourselves in our work was how we can obtain uniform characterizations of the expressive power of GNNs. Yeah? And by uniform, what do I mean? I'm going to mean the following. So let's imagine that we have an MPGNN M with T layers, as we have seen before. And we are going to write M of U for the embedding obtained by M on node U after T iterations. Then we say that M, the message passing graph neural network M, is able to express a first order formula phi of X with one single free variable X if for every graph G, and this is the uniform part, right? So for every graph and node U, we have that U satisfies the property expressed by phi over G if and only if the embedding, when I look at the embedding of U, in its first component, it contains a 1. So in a way, it tells me the message passing graph neural network expresses formula phi of X if I can, for any graph and for every node U, I can signal which nodes satisfy this property with a 1 in the first feature of my vector. Yeah. I hope this is clear. Otherwise, please feel free to ask. Yeah. So it's a different thing, right? So it's not that we are trying to distinguish nodes in a graph. We're saying that we want to understand which kind of properties of graphs can be expressed with graph neural networks. And as a starting point, we focus on those properties that can be expressed by first order formulas. Yeah? So we managed to obtain upper and lower bounds here for the expressive power of message passing graph neural networks in terms of logic. So let's imagine that phi of X is a formula in C2 that has some important syntactic property, that is that we call them guarded. Yeah, and I will explain afterwards what is guarded. If my formula comes from this fragment, yeah, and it is guarded, then there is a message passing graph neural network that can express it. Yeah, so the properties that can be expressed in this logic are also identifiable in a uniform way by message passing graph neural network. When a formula is guarded, whenever I say that there exists an element, this element is linked by an edge to the value, to the variable set where I'm evaluating my formula. So I cannot say there exists a y such that phi of y. Every time that there exists a y, I have to say there exists a y which is a neighbor of me where the formula phi holds. Yeah, that's the idea of the guarded fragment. So for instance, the following formula is guarded, the formula that we saw before, right? There exist at least 3 y's such that are linked to x, where I'm evaluating the formula, they are red, and it is not the case that there exists an x that is linked to y and blue of x. On the other hand, this is a C2 formula that is not guarded. This C2 formula is saying there exist 3 red nodes in the graph. Yeah, there is no way I can say this in my guarded fragment. Yeah? So the lower bound tells us that every formula in this fragment can be expressed. But this is only a lower bound, right? It tells us everything that can be expressed here can be expressed as an MPGNN in a uniform way. But what if I have a formula with 3 variables, yeah, or a formula that is not guarded, yeah? Can it be expressed? And the answer is no, at least for properties that are expressible by first-order formula. So if I have a first-order formula that can be expressed as a message-passing graph neural network, then phi has to be equivalent to a guarded C2 formula. So restricted to the first-order expressible properties, MPGNNs can express precisely the fragment consisting of guarded C2 formulas. These are the properties that we can detect with message-passing graph neural networks. Yeah? Now, only guarded C2 formulas can be expressed by message-passing graph neural networks. And we asked ourselves whether there exists a meaningful, yeah, and not only meaningful, ideally practical as well, extension of message-passing graph neural networks that can express all formulas in C2. That is, even those that are not guarded, like there exist 3 red nodes in the graph. Yeah? And it happens to be the case that indeed there is this natural extension. The natural extension, which actually exists in the empirical literature, is that we have to extend message-passing graph neural networks with what we call global readouts. Yeah? And the global readout is an extension of the previous architecture. So that is, I aggregate over neighbors, I combine with my previous value, but in this case, I also aggregate over all nodes in the graph separately, yeah, with a different matrix, yeah? So I aggregate over neighbors here, I aggregate over all nodes in the graph, yeah? And then I do the whole combination of these values, yeah? So in fact, these message passing graph neural networks with global readouts are capable of capturing in a uniform way every formula in C2, including those that are not guarded. And in fact, you don't need global readouts in every layer of the message passing graph neural network. Only one global readout at the very last layer suffices for this. So an open question that we left in this paper is whether the converse is also true. If you have a formula in FO that can be expressed as a message passing graph neural network with global readouts, can this be expressed in the 2-variable fragment with counting quantifiers? And there is a recent paper, very nice paper, which shows that this is not the case, and this was very surprising to me. So there are formulas beyond C2s that can be expressed in first order, that can be expressed with message passing graph neural networks with global readouts. Yeah? So I'll stop here for some minutes to see whether there are questions about this.
Any questions?
Yes, hello, good evening. Am I audible?
Yes, please. Please
Sir, so my question was the properties that you explained in the case of uniform, when we are considered. So are these, can we means examine or monitor all these properties under the non-uniform case as well, or we are taking some help of some transformations techniques and then bringing our data to a under uniform condition, and then we are studying these properties.
No, every property that can be expressed in the uniform way, we know by the results that we presented that every property that can be checked in a uniform sense can also be expressed in the non-uniform sense. But there are properties that can be checked in the non-uniform sense that cannot be expressed in the uniform sense. And these properties are precisely the properties that are not guarded. Yeah?
Okay.
Yes.
Thank you, sir.
Can I ask a question?
Yeah, for sure.
Hi. Hi. I was just wondering, you mentioned this first order logics and two variable fragment of first order logic and then guarded first order logics. I was wondering that modal logic sits inside that, and it has very nice computational phenomena. So is there any such kind of relationship developed in particular in terms of modal logics? What can they
Yes.
that particular fragment?
Yeah, actually guarded C2 is precisely what people call graded modal logic. That is modal logic extended with counting quantification. And then C2 is modal logic extended with what people call global modalities. So that's in fact the way in which we prove the results, by connections to these modal logics, because these modal logics are unary, then you can prove things inductively very easily.
Yeah, exactly. Okay.
Mhm.
Thank you.
Yep.
Any more questions?
We can move on then.
Yeah, sure. I think so.
Okay. So the second topic that I wanted to talk about is the expressive power of transformer encoders. This is something that we did 2 years ago. So I will try to define what these things mean for us, right? Before getting into the results. So I guess that we all know at this moment what transformers are. They are a deep learning architecture that acts as a sequence-to-sequence transducer. So we are given an input, a sequence of feature vectors, and it outputs another sequence of feature vectors of the same size, the sequence, right? Not necessarily the dimension of these vectors. So the motivation that we had for this work is like, what are the computational limits of transformers? Yeah, which languages, since transformers are transducers, which languages transformers can transduce, and in particular, which languages can they recognize? Yeah. Okay, so what is a transformer? For us, right? First of all, we are only going to talk about transformer encoders. So Arijit mentioned earlier that we had these results about 6 years ago on attention is Turing complete. Transformers are Turing complete, right? But for Turing completeness, you need your transformer to have a decoder as well. So we wanted to isolate what was the implications of the decoder from those of the encoder only. Yeah. So we studied here what is the expressive power of encoders only. The difference is that the decoder can increase the length of the sequence with which you are working, while the encoder just takes a sequence and transforms it into a sequence of the same length. Yeah. So what is a transformer encoder? A transformer encoder is a stack of encoder layers. And encoder layers can be of two kinds: standard, like the ones we're seeing here, and ReLU. Yeah. In standard transformer encoders, how are they defined? They are defined by three different matrices of parameters: A, B, and C. AB takes a feature vector of size D and computes a new feature vector of size D. And C takes two feature vectors of size D and computes a new feature vector of size D. Yeah. So the transformer encoder receives this sequence B1 to B sub n of feature vectors of dimension D. Yeah. And the first thing that it does is to perform attention. Yes. How is attention performed? So for each pair B sub I and B sub J or B sub L, yeah, B sub I and B sub L, I will first apply transformation A on B sub I. Sorry. I will first apply transformation A on B sub I, like here. I will apply transformation B on B sub L, here. I will take the dot product of these two things, and I will look at the value that I obtain. So I will stick here to B sub I. I will be looking at B sub I. So I will do this for every L that is different from B sub I. Yeah, I will do this for every pair. No, not only different, for all of them, including B sub I itself. And I will look at this value. And I will see for which value L, this, for which index L, this value, this dot product is maximized. Yeah. And where, sorry. And when this, this dot product is maximized, let's say in K, I will define A sub I to be simply B sub K. So B sub K was the one that maximized this, so I will put B sub K here. Yes. Now, there could be several indexes that maximize this value, so I'm going to break ties. How I'm going to break ties? I'm going to just choose the leftmost element in this set of the ones of the indexes that maximize this. Yeah. And finally, once I have A sub I, that is the value of B sub K that maximizes this attention, I will combine it again with B sub I because I don't want to lose information about my B sub I. So I will combine this B sub K, which is A sub I, with B sub I. I will combine it through the linear transformation C. And this will be the output of my standard encoder layer. So the attention mechanism here that we are using is often known as unique hard attention. Why it's unique hard attention? First of all, it is hard in terms that only elements that maximize this dot product are considered. You could also have a soft attention in which all elements are weighted in a way, and they are a weighted average of this value is considered. Here, we're only considering those that are maximize this value. And it is unique because ties are broken by choosing a single element. So we are not trying to average them. We are choosing a single element, in this case, the leftmost. So this is called unique hard attention. And a ReLU encoder layer does something very simple. It applies, for every vector, it applies the ReLU function, which is the maximum between 0 and x, to the kth component of this feature vector, right? So I will just replace negative values by 0. No? So as I said, a transformer encoder is just a stack of several encoder layers. They can be standard or ReLU. Yeah. So we want to use this architecture as a way to recognize languages. But here in the input, the transformer doesn't receive letters from a finite alphabet. It receives feature vectors, right? So we have to have a way to represent, to encode letters as feature vectors. And also, we want to encode the position of the element because the encoder, the transformer encoder, doesn't have a way to understand that this position appears before this one, which is very important when we are recognizing languages, right? So we are going to use the notion of encodings. An encoding, so we are given a finite alphabet sigma. An encoding of this finite alphabet sigma is a function that to each letter it assigns some feature vector in d dimensions. Yeah. And a positional encoding is a function p that to each natural number it assigns a feature vector, say in e dimensions. Yeah. So we want transformers, encoders, to be able to recognize languages. And what does it mean to us? This is probably the most important slide in this part. So imagine that we have a language L that is a subset of sigma plus, so we don't consider the empty word. So our language L is a subset of sigma plus, and we have a transformer encoder T with unique higher attention. Then we say that L is accepted by T if there exists some way to encode the alphabet and there exists some way to encode the positions, such that for every word, for every non-empty word, we have that if we encode the word in this way, in which way? So we will take the encoding that consists of the alphabet encoding of the letter A sub I, plus the positional encoding of element I here. This is what is given as input to the transformer. Then I will look at the output, W1, Wn, and I'm going to say, if Wn is positive, or say the first component of Wn is positive, then that happens if and only if the word is in the language. That is, I have a way to signal in this last feature vector, in saying its first component, I have a way to signal when all this word that I have encoded in this way belongs to the language. Yeah. Hope this is clear. So in 2022, Hao, Anglin, and Frank proved a very interesting upper bound for this. It says that every language that can be accepted by a transformer encoder with unique higher attention is in the class AC0. Yeah. For those who don't remember exactly, AC0 are those languages that can be accepted by Boolean circuit of constant depth and polynomial size. Yeah. Very importantly, AC0 is one of the few classes for which we know that some languages do not belong to this class. In particular, the parity language, that is the language of over the alphabet 0, 1 of words that contain an even number of ones, is known not to be in this class. Yeah, so it's given us an upper bound, right? It's telling us if a language can be accepted by transformer encoder, then it is also accepted by a family of circuits of constant depth and polynomial size. Yeah. Yes. So there was an obvious question here, right? So what about the lower bound? Is it true that every language in the class AC0 can also be accepted by a transformer encoder? And we showed that this is not the case. So the upper bound is not optimal. There is an AC0 language, yeah, that is not accepted by any transformer encoder with unique higher attention. Yeah. So given this, we have an unsatisfying situation here. We have an upper bound that is not optimal, right? And we wanted to understand which fragment of AC0 in a way can be expressed by transformer encoders. Yeah. And as a spoiler, we don't have a full characterization, but we have a nice lower bound at least. So there is a very well-known characterization of those languages that can be accepted by AC0 circuits. These are the languages that can be expressed in first-order logic with arbitrary numerical predicates on positions. Yeah. So I can say this position is prime, these two positions sum to this third position, and so on. I can use this in my first-order formulas. First-order formulas talk about the labels of the letters and the order, right, in which the string is given. And then I also have these arbitrary numerical predicates. So what we showed is that, well, we know that since not every AC0 language can be recognized by a transformer encoder, we couldn't capture all these first-order logic with arbitrary numerical predicates. But at least we can capture a very interesting fragment. So let's say that L is an AC0 language that is definable in first order plus arbitrary monadic numerical predicate. So I don't have sum, I don't have multiplication, yeah? I only have the numerical predicates that are monadic. For instance, this position is prime, this position is even, and so on, yeah? Then in this case, and this is what people have called monadic AC0. Then in this case, L is accepted by a transformer encoder with unique hard attention. Yeah. So monadic AC0 is contained in transformer encoders, and we don't know whether they are equivalent. We highly suspect that they are not. And then the question is like, what is the boundary for languages that can be accepted by transformer encoders inside AC0? So our proof idea here, and I'm gonna mention this because there was a similar question before regarding modal logic. What we do is we apply the very famous Kamp's theorem and rewrite the first-order formula that defines cells as a formula in linear temporal logic, LTL. And then we inductively show that every language definable by an LTL formula is accepted by a transformer encoder with unique hard attention. It's much easier to do it over LTL because LTL formulas are unary, so we can perform induction. So there is a nice application of this result. There is a seminal result by Barrington, Compton, Strobing, and Terian that says that every regular language in AC0 is definable. If you have a regular language and this language happens to be in AC0, not every regular language is in AC0, of course, right? There are regular languages that are NC1 complete. But every regular language that is in AC0 is definable in first order with monadic numerical predicates. So as a corollary to our results, we obtain that if L is a regular language in AC0, then L is accepted by a transformer encoder with unique hard attention. But one could also, and in the literature this has been done a while, one could also consider a different attention mechanism. So we were always looking at this signal, right? What is the dot product between the value of A times B sub I, dot product B sub L? And we were looking at the one that maximizes this, and if there were ties, we were choosing the leftmost one. But we could also take the average of those values that maximize the attention, right? So we could define the average in this way, and this is what people have called average hard attention, yeah? So it's still hard because it's based on the maximum, but it's not unique, it's average, yeah? And interestingly, once you do this small modification to the attention mechanism, then the expressive power of the transformers increases a lot. In fact, transformers with average hard attention can recognize languages in TC0, which is the extension of AC0, where now circuits are allowed to use the majority gate, a gate that takes several inputs and it tells us whether the majority of them are 1. And what we showed is that if you have the binary alphabet, 0, 1, and you have a permutation closed language over this alphabet, this will be accepted always by a transformer encoder with average hard attention. Yeah? So as a corollary, we obtain that both majority and parity are accepted by transformer encoders with average hard attention. Yeah. So why? Because they're both permutation closed languages over the binary alphabet. All right. So I will stop here for the time being, just in case there are questions about this this second section.
Any questions?
No?
No, I think we can move forward.
Okay, I will move on. Okay, so in this last section, I will cover ideas of how to use logic to define declarative query languages for explaining machine learning models. But since things are quite complex in this realm, we are gonna try to explain very simple machine learning models, so-called decision trees, right? So what is the explainability problem? The explainability problem in machine learning is as follows. We are given a model, a machine learning model, which in this case is Boolean. So it's a Boolean function that receives inputs a vector of zeros and ones, and it outputs a 0 or a 1. And the question is, how can we explain the output of this model on E? Why is this model outputting 0 or 1 in this particular input? Yeah. So a bit of notation, we are going to assume that the set of features received by the Boolean model M is X, capital X, composed by small x sub i's, yeah, x1 to x sub n. An input to the model is then a function that assigns a 0 or a 1 to each feature in X. And we are going to write M of E for the output of M on input E. Yeah? So how people have tried to explain the decisions taken by machine learning models? Well, there use different kind of queries, yeah, and these are explanatory queries. So one of them, which is quite popular, is the counterfactual explanations. So we are given a Boolean model M over a set X of features, in this case, an input E, and we're going to call a subset of the features, a subset Y of the features, a counterfactual explanation for this input given by M and E, if when I flip the values in Y, I change the classification of the Boolean model of the machine learning model that I have, right? So in a way, it's saying, oh, I obtained this this decision by the machine learning model. I'm not satisfied. What do I have to change, right? Well, you have to change this and this in order to flip the decision made by the model. And in general, well, we look for counterfactual explanations that are minimum, right? There is no counterfactual explanation of smaller size. Another kind of explanations that people have looked are so-called sufficient reasons. So again, we are given a Boolean model M over a set X of features, an input E, and a subset of the features Y, in this case, is a sufficient reason for the pair M and E if whenever I change the values outside Y, the output of the model continues being the same. So the output of M on E is invariant to the interpretation of the features outside Y. So in a way, this is telling me you're obtaining this result because the values of these features are enough to obtain these results. Yeah, your paper was rejected because it exceeded the number of pages, right? So it doesn't matter whether my paper is good or not. Only this feature is justifying this. By just looking at this feature value, I can justify completely why the paper was rejected. Yeah, and of course we look again for sufficient reasons that are minimum. There is no sufficient reason of smaller size, and when this is complicated to compute, we are sometimes satisfied with sufficient reasons that are minimal. There is no sufficient reason set that is strictly contained in Y. Yeah, so I cannot continue reducing the sufficient reason Y by removing feature values. So let's consider an example here. Consider the model M that only takes the disjunction of x1 and x2 and an input that assigns value 1 to each one of x1 and x2. The minimum counterfactual explanation for M and E is both x1 and x2, because I have to flip both values in order to change the value of the output, right? I have to flip both x1 and x2 to 0. On the other hand, if we look at minimum sufficient reasons, there are two of them. Because if x1 is 1, then I know that the output is 1 regardless of the value of x2. And the same for x2. Yeah? So this is how the notion of counterfactual explanation and minimum sufficient reasons differ. Now, what's the need? Well, these are just two examples of explainability queries. But many other explainability notions have been proposed in the literature. Yeah, we have a myriad of explainability notions, queries, scores, and so on. Yeah, so the logical community has handled this challenge by developing declarative query languages. So declarative query languages that are general purpose languages that allows us to express explainability notions in a general way, and then we can process from this language. Imagine SQL, for instance. We have SQL. Instead of dealing with this query in a database, you specify your query, and then you have an engine that can process any of these queries, yeah? Relational algebra queries. So declarative query languages for explainability tasks would help in, first of all, allowing more flexibility in writing queries for different applications, yeah? Providing a clear syntax and semantics for such queries, making explainability tools more accessible for practitioners because now the language is declarative, yeah? And opening a path for optimization of explainability queries as it has happened in other areas of theoretical computer science. So the first thing that we have to do in order to design our query language is to be able to represent Boolean functions with a logical model. Yeah. So we are going to represent a Boolean model M over a set X of features with of size n as a logical structure A sub m. Yeah, which is defined as follows. This is the domain of my structure. The domain consists of all tuples, yeah, all tuples of size n formed by zeros, ones, and what we call an undefined value bottom. Yeah, this is an undefined value. So this is the set of all partial inputs. Yeah, those inputs to the model that may have some undefined values. And then we will have two relations on these tuples. The first one is the binary predicate that we call completions that contains pairs E and E prime of partial inputs such that E prime is more complete than E. So for instance, the partial input 1, 0, undefined is more complete than 1, undefined, undefined, because this partial input can be obtained from this partial input by replacing the middle undefined value by 0. Yeah? And finally, the unity predicate pos is interpreted as the set of positive inputs. That is the set of full inputs without undefined values that are classified positively by the model. So our logic our interpretability logic that we call a FOIL is nothing else than first-order logic over structures of this form that represent Boolean functions. So it's a way to represent Boolean functions with logical structures. So what can we express in FOIL? Well, we can express interesting stuff. So for instance, we can say that which tuples do not have undefined values. Let's call them full instances. Yeah? An instance is full when an instance X is full when there exists no Y, yeah, that completes X and is different from X. Yeah. So if I have an undefined value, I can complete it. But full instances are those that cannot be completed further. Yeah. I can say that Y is a full completion of X. So I say that Y is a completion of X. Yeah, I obtain Y by replacing undefined values in X with constants, and Y itself is full. It cannot be completed further. We also can define the pairs of same class full instances. So we can say this instance X and Y are both full, yeah, and they're both positive, or they're both negative. Yeah, so they belong to the same classification class. Now, the binary predicate sufficient reason then when X is a sufficient reason for Y. Well, first of all, Y has to be full. Yeah. Second, X has to be containing Y in the sense that X is obtained from Y by undefining some features, yeah, the ones that do not matter. And then every full completion set of X is in the same class as Y, right? So if Y was positive, every full completion set of X is also positive. So now we can say, for instance, that X is a minimal sufficient reason for Y. How do we say that? We say that X is a sufficient reason for Y, and for every set, yeah, that is properly contained in X and is also sufficient reason for Y, we have that set is X. Yeah? So I hope this is clear enough. Now, I think that this is a very simple, elegant definition of an interpretability logic. You just define a logical structure for a Boolean function, and then you apply first-order logic over it. Yeah? The problem with this is twofold. First of all, FOIL is not capable of expressing some useful explainability notions used in practice. So it lacks all the expressive power that we need. And second, there is a complexity issue. The evaluation complexity of FOIL is prohibitively expensive even over simpler models. Yeah? So let me try to explain why this is the case. The first issue is expressiveness. There is no formula phi of xy in FOIL that checks whether X is a minimum sufficient reason for Y over the class of decision trees. Yeah? So we can check whether X is a minimal sufficient reason of Y, but we cannot express the stronger and more interesting in practice notion whether X is a minimum sufficient reason for Y. There exists no sufficient reason with less undefined features. Yeah? So intuitively, FOIL cannot compare the cardinalities of such features. And second, for every K, there exists a sentence phi sub K in FOIL for which the evaluation problem over the class of decision trees is sigma KP complete over, is sigma KP complete. Yeah. So basically, evaluating this language even over the class of decision trees is complete for each level of the polynomial hierarchy. Yeah? So this is, of course, not ideal. Yeah? So the problem here is that we have conflicting requirements, right? On the one hand, we want a more expressive logic, and on the other hand, we want an easier to evaluate logic. So the only way in which we can do this is by both extending and restricting the logic, yeah? And this is a difficult balance that we have to strike. So what efficient means in this case? Well, first of all, it cannot be polynomial time, because evaluating minimum sufficient reasons over decision trees is co-NP complete. Yeah, so even for our most desired explainability notions to evaluate it over the very simple class of machine learning models composed by decision trees is computationally co-NP complete. But that's not such a big problem, yeah, because decision trees are not so large in practice. So what we said is that if a formula can be evaluated as a Boolean combination of NP languages, this is good enough for us because then we can use SAT solver technology to evaluate it. Yeah, and in fact, this is what we did. So I will not be able to present the language because I have limited time, and I also want to leave some time for conversation. But basically, what we did is to both restrict and extend the language in a way that the resulting language that we call decision tree foil is capable of expressing many of the useful explainability notions often found in practice, including minimum sufficient reason, including minimum counterfactual explanations, and several others. And interestingly, for this fragment, the problem of evaluating phi over decision trees can be solved by a constant number of calls to an NP oracle. So we can use SAT solver technology to evaluate these queries over decision trees. And we actually did a full implementation of that, which shows very promising results. Yeah, so we have a SAT solver implementation of this language that can be applied over decision trees. And more in general, we have extended this not only to decision trees, but to the more general class of deterministic and decomposable circuits in negation normal form, which subsume decision trees, but they also subsume many other classes, including binary decision diagrams. Yeah. And with this, I would like to finish and thank you for your attention so that I can also receive questions.
Yeah, thank you for the excellent talk. So, questions from the audience?
If I may deviate briefly from today's topic, I have a couple of questions from your ICML paper on EH rank and COT. Like, I am not very certain if there will be any further meeting, so I am asking it here. But I will try.
Yeah. Okay.
The core proof for constructing the decoder while simulating the decision tree was actually implemented by a tree traversal, of course, keeping the criteria of finding the minimum value from the permutation of A queries. Now, that traversal, can that traversal be elevated to a general simple graphs? If so, what are the notion of complexity that can replace the rank, the notion of rank over there?
Oh, wow, that's a very difficult question. I don't know, but I would be very interested in trying to think about it. Why can you send us an email with that question to the three authors, and we will try, because we are precisely in the process of writing the journal version of that paper.
Okay.
Yeah, I would appreciate it because this is something that I have to think about it. I mean, it's not so easy.
Well, so there is a technical part from the proof that I have noticed that the construction skips the standard value projection matrix from there. So have we used that? Can that decrease the size of embedding dimension or make the trivial assignment for the FFN matrices?
Oh, again, yeah, why don't you send us a message and
Okay,
we would
sure,
be
sure.
happy to discuss about it. Yeah, but I would have to dig into the paper again to start understanding this stuff.
Okay.
Yeah, sorry, I was not prepared for that.
So I completely agree. I will contact you later.
Yeah, please do. Yeah.
Yes.
Debanjan, you had another question, no? Or just one?
I had another, but I was like,
No, ask. I don't think. Don't have
okay,
to.
this is a very broad question. Like COT was defined using decoder steps following the Will Merrill's constructions, but in
Yeah.
practice there are also some other prompting techniques like tree of thoughts and others. So is there a way of theoretically encode those in decoder steps?
I have never seen this, but this is very interesting. No, I don't know. I would have to think about it, but it's yeah. So you're asking whether tree of thought, well, it gives you any gain, right, in terms of expressive power somehow, no?
Yes. And how can we define in terms of the decoder steps? Like,
yeah. No. I haven't thought about it. Yeah, very interesting.
okay. I will
Yeah.
surely contact you and all
Yeah,
three of
please.
you.
Yes.
Yeah.
So from where are you?
I am from Indian Statistical Institute. I am a
Okay. Cool.
Any other questions? So one question that I have is like, so I slightly work in this, look into this area of what is called like Boolean functions, and we analyze through Fourier analysis techniques. So there sometimes that is of interest is okay. So maybe you won't be able to reconstruct the whole function, but approximately reconstruct in terms of Hamming distance. Okay, so like fraction. So
yeah.
are these notions, approximate notions, have also been explored?
No, not at all. And yeah, you mean for the last part of the talk, right?
Yes. Yeah.
Yes. No, not at all. And also something that we're starting to explore now is counting mechanisms, right? Because, for instance, if you have Shapley values, Sharp scores, yeah, you want to count how many assignments, and this is something that we don't know very well how to do at the moment.
Right.
Yeah, but approximations might also be of interest.
Right. But so the thing is like, if I like this area like studying Boolean function with Fourier, that I also started in like late 80s with work of
Yes.
So, but those things have not been, you said, not been explored in this area that much. Like
No, not at all.
approximately
Not at all.
reconstructing.
Yeah, not at all.
What about like Fourier analytic techniques? Are those used also?
I have never seen this.
More, okay.
Yeah, I've never seen it. No.
Which is yeah. Okay. Thank you. So, any other questions?
Let me ask. So, yeah.
So this is Sujata Ghosh, who's a professor at ACMU.
Yeah, so I'm coming back to the logic thing. You mentioned this relation, the proof of that AC0 thing together with the first order logic, and you use some LTL techniques. So
Yes.
I was wondering what led you to use those LTL techniques coming from FOL.
No. Yeah, in that case, because we have first order logic with arbitrary monadic predicates, right?
Yeah.
And we have to do an inductive proof. And the problem is that when you do it and transformers are unary, right? They only select, yeah. So we couldn't do an inductive proof on first order itself, because then you would get a binary formula when you open a unary formula. So the only way we could deal with this is via LTL. Of course, this causes an astronomical blow up in terms of the size of the formula. But this is an existential result. There exists a transformer, so we don't really care, and we kind of swept this under the rug. But it was a way for us to turn the formula into a sequence of unary formulas that we could handle by induction.
Okay. Okay.
Yeah. And the monadic predigats are not a problem in that case, because they're monadic, right?
Yeah, sure. That I understand. Yeah. Okay. Thank you.
Any other questions? Okay, and so we thank the speaker, Professor Pablo Barceló. It's an extremely nice talk, and we had a very nice time hearing. Thank you for give a talk.
No, thanks very much for the invitation. Yeah, it's the first time that I see a country which is has 7 hours and 30 minutes difference from you know that, yeah. We are at 7 hours and 30 minutes difference from Chile.
Okay.
Yeah. All right, thanks very much.
Thank you very much.
Yeah.
Thank you. Bye.
Bye.